In this video tutorial, we will introduce the concepts of acids and bases. Most students are familiar with the term acids, but maybe not so much with bases. Well, an acid is a substance that dissociates in water, so that means when it dissolves in water, it breaks up, producing one or more hydrogen ions, shown with the symbol H+, because it has lost an electron. On the other hand, a base is a substance that dissociates in water, so dissolves in water, and then breaks up to form one or more hydroxide ions, that's OH-. So if you look at the list of acids I have over here, you'll notice that every single one of them has an H+ ion inside the chemical formula. So when dissolved in water, we say it's aqueous. The water molecules will then split these guys up, releasing H+ ions and Br- ions. In this case over here, releases one H+ and an HSO4 ion. And over here, H+ is released and a ClO4-. It is this H+ ion that gives acids its acidic properties. So the more H+ ions floating around in solution, the more acidic that acid is. The opposite is also true. If there are fewer H+ ions floating around solution, then it's going to be a weaker acid. So something like citric acid that you would find in orange juice or lemon juice, or something like vinegar, acetic acid, things that we would use in our cooking or food products will have fewer H+ ions inside of it. It would be less acidic than something like hydrochloric acid. All right? So hydrochloric acid we would use in our stomachs to help us digest food, whereas acetic acid, vinegar, or citric acid, lemon lime juice, those things are used to flavor our foods because they're weaker acids. I would certainly hope that you do not flavor your food with hydrochloric acid, a much stronger acid. Over on the right-hand side, we have a list of bases. You'll notice that every single one of them has a hydroxide ion in their chemical formula. So during the process of dissociation, when they dissolve in water, making an aqueous solution, they will release a lithium ion, but also the hydroxide ion. In this case over here, the potassium and the hydroxide will split up, while the barium and the hydroxides will also split up. Now, keep in mind that this last reaction over here is a skeleton equation. It is not balanced. In an unbalanced equation, the barium hydroxide would release one barium, but it would release two hydroxide ions. Now, just like acids, the more hydroxide ions floating around your solution, the more basic the solution is going to be. Furthermore, the presence of these free moving ions, now that they're free to move around, they're no longer stuck in position, allows them to conduct electricity in their aqueous form. So aqueous meaning dissolved in water. If you recall from an earlier lesson, solutions that can conduct electricity are known as electrolytes. As I mentioned earlier, most students are familiar with the term acids. They know that it tastes sour, so lemon juice, lime juice, orange juice, citric fruits. And some may be aware that acids conduct electricity, which is where they probably heard the term battery acid. Now, acids can react with metals to produce hydrogen gas. So here we have magnesium reacting with hydrochloric acid in a single displacement reaction. Please press pause and try and predict the products of this reaction. When you're ready, press play and we'll take it up. So in this single displacement reaction, the magnesium is going to bump out the hydrogen because we always have to have a positive and negative partnership. The old partners were positive and negative. The new partners must be positive and negative. We can't combine the magnesium and the hydrogen together because the two positive charges would repel. So we need to check and see if the magnesium can displace or push out the hydrogen and take its place, thereby bonding with the chlorine instead. For that, we would consult our activity series. Only elements at the top will be able to bump out those at the bottom. So here we see magnesium is more reactive than the hydrogen, which means the magnesium is allowed to displace or bump out the hydrogen. We now have magnesium and chlorine bonded together. Don't forget to zero sum, MgCl2. And of course, hydrogen is not allowed to be by itself because it is diatomic, so don't forget the number 2 subscript here. And that is one way in which acids react with metals to produce hydrogen gas. Acids can also react with carbon-based compounds to produce CO2, but we'll look at those reactions in a future course. As we mentioned, common examples or uses of acids in the home: citric fruits, so lemons, limes, oranges, vinegar, acetic acid, carbonic acid is typically found in soft drinks, and much, much more. Acids are quite commonplace in our everyday lives. Now, the term bases may not be as familiar with students, but you're definitely familiar with their uses in the home. Quite often, our cleaning agents are basic in nature, so oven cleaner, baking soda, glass cleaner, even a bar of soap is typically going to be basic. Many medications are also basic, which helps to explain why so many taste bitter. Again, due to the freely moving ions, Bases can also conduct electricity, where the greater the concentration of the ions, the more conductivity it has. Finally, the reason why most cleaning agents are basic in nature is because they're able to react with proteins and other organic compounds in order to break them down to smaller molecules. So large molecules like fats and grease can be broken down by bases into smaller molecules, making it easier to clean them off. Now, we can create acids by taking a nonmetal and then burning it. As in most cases, when you burn something, you need oxygen. By burning a nonmetal, like in this case sulfur, with oxygen, you create a nonmetal oxide. So in this case, sulfur plus oxygen creates a sulfur oxide. From there, you take the nonmetal oxide, add it with water, and then you produce an acid. So as an example, gasoline quite often contains some sulfur atoms inside. When we burn gasoline, we also burn that sulfur, creating a nonmetal oxide. This nonmetal oxide comes out the exhaust pipe of cars, eventually ending up in the atmosphere. Guess what else is in the atmosphere? Water, and that's where we get sulfuric acid coming down as acid rain. Another component of acid rain is carbonic acid. That is produced from the carbon dioxide in the atmosphere. Carbon, nonmetal, oxide, nonmetal oxide. So when you take a nonmetal oxide, combine it with water, you will make an acid. And that's how soda stream machines work in order to give you fizzy carbonated water. They pump canisters of carbon dioxide, mix it with the water, in the process producing carbonic acid. So we call these carbonated drinks. Now, you can think of acids and bases as being opposites of each other. If we use a nonmetal oxide to produce an acid, then we must use a metal oxide to produce a base. Again, take a metal, burn it, and create a metal oxide. From there, just add water, and now you have a base. When it comes to their nomenclature, or naming them, bases are fairly straightforward as they follow the polyatomic naming conventions. So lithium hydroxide, LiOH, or beryllium hydroxide, BeOH2. Just make sure that you follow the zero-sum rule. So press pause and take a moment to fill up these four. When you're done, press play and we'll take it up together. Alright, so MgOH2, magnesium hydroxide, NaOH, sodium hydroxide, aluminum hydroxide. Make sure you remember that aluminum has a 3+ valence charge, so when you zero sum, I need 3 of these hydroxides. Don't forget to keep the brackets on over here because we're referring to 3 hydroxides and not just 3 hydrogens, so the brackets are necessary. And finally, calcium hydroxide. Calcium has a 2+ charge, so when I zero sum, I'm going to need 2 of these hydroxides in order for this to zero sum properly. Unfortunately, naming acids is a little more complicated. There are 2 naming systems that we're going to be looking at. The first is the binary acid, while the other one's called an oxyacid, or sometimes called an oxoacid. These ones are called binary acids because binary means 2, and each one involves only 2 elements: hydrogen and chlorine, hydrogen and sulfur, hydrogen and fluorine, etc., etc. While these ones are called oxyacids because every single one of them contains an oxygen inside. Now, when it comes to binary acids, they follow this following format. Put the prefix hydro, change the suffix to an ic, and you've got an acid. So over here we have a Cl, chlorine, making it hydrochloric acid. H2S is hydrosulfuric acid, while HF is hydrofluoric acid. Now going in the opposite direction, we know there's always going to be an H in the front with a 1+ charge. In this case, it's hydrophosphoric acid, so that means there's a phosphorus atom over here. Hydrogen has a 1+ charge, phosphorus with a 3- charge, so I need to have 3 hydrogens for this to zero sum properly. For these other 2, they all only have a valence charge of 1-, so it's already zero sum, no need for any subscripts. Hydroiodic acid, Hi, high, and hydrobromic acid, HBr. Moving to the other side, we see that they have removed the hydro prefix. Since this is a sulfate ion, we name it sulfuric acid. The iodate turns into iodic acid, while the phosphate becomes phosphoric acid. We can then repeat the pattern on this side. So bromic refers to the bromate, PrO3 with a 1- charge. We start off with an H, 1+ charge, and the bromate, 1- charge. Everything's zero sum, no need for additional subscripts. We're good. Nitric acid refers to the nitrate ion, NO3, 1-, giving us HNO3, zero sum, that's good. And chloric acid gives us HClO3, zero sum, and that's good. So you'll notice that when it comes to binary acids, we only deal with 2 elements at a time, while oxyacids must deal with the polyatomic ions, the ones that contain oxygen inside of them. Binary acids have the prefix hydro, while oxyacids do not have the prefix hydro. Otherwise, everything else about it is the same. Ic, acid. Another reason why you can think of acids and bases as being opposites of each other is because they cancel each other out in a chemical reaction known as a neutralization reaction. Looking at this reaction, you can see that it is a type of double displacement reaction, where they each switch places, providing a brand new partner. Now, if you recall from a previous lesson, I recommended that you stop thinking of water as H2O and start thinking of it as hydrogen hydroxide instead. This will help you when you're trying to predict the products of this chemical reaction, because now the hydroxide makes a new partner with the hydrogen to form water. And this is certainly helpful when you're trying to balance the equation as well. So during a neutralization reaction, an acid and a base will cancel each other out through a double displacement reaction, producing an ionic salt and water. Now, when we use the word salt in chemistry, there are two meanings. There's NaCl, which is table salt, the type that we use and put in our food. But there's also ionic salt, which is a very general term we like to use in chemistry to describe an ionic compound. Alright, so table salt, the type that we put in our food, sodium chloride, and then ionic salt, just a general term meaning ionic compound, usually one that dissolves well in water. Now, as we saw earlier, acids can react with metals in a single displacement reaction, so please predict the following chemical reaction. Press pause, when you're ready press play, and we will take it up. Alright, so this is cation single displacement, where the cations are going to displace each other. Again, check the activity series. Magnesium is higher, so it can bump out the hydrogen, creating the brand new partner of magnesium and sulfate. Don't forget to zero sum. In this case, it's fine, 2 and 2, so we don't need any subscripts. But hydrogen is, of course, diatomic, so don't forget the 2. Now, the problem with neutralization reactions is that it's hard to tell when the reaction's over, or even if the reaction occurs. That's because acids tend to be clear, colorless, transparent, aqueous solutions, and so are bases, clear, colorless, transparent, aqueous solutions. And when they react together, you make salt water, which again is clear, colorless, transparent, and aqueous. So here you have a situation where all four substances look like water. So how can you tell that the reaction has happened? Now, I don't recommend that you lick it. Obviously, the acid will taste sour and the base will taste bitter, but they both taste like burning, so that is not recommended. Instead, we can use something called an indicator. This is a chemical substance that changes different colors in the presence of an acid or a base. Now, there are many different types of indicators out there, but a cool one you can make at home is found in red cabbage. There is a chemical inside these red cabbages called anthocyanin that changes color depending on how many hydrogen or hydroxide ions are floating around your solution. The anthocyanin turns a little more bluish-greenish if you expose it to hydroxide ions, but becomes a little more pinkish-reddish if you expose it to hydrogen ions. And so we refer to this chemical as an indicator because it indicates if it's going to be an acidic or basic solution, because it would be hard to distinguish between an acid and a base without it. Now, what we've learned so far is called the Arrhenius definition of acids and bases. There are many other definitions, and depending on what you're studying, one definition may be more useful to you than another. But for this course, we'll be looking at the Arrhenius definition and something called the Bronsted-Lowry definition. You see, there are a few problems with the Arrhenius definition. Although this theory works in most cases involving acids or bases dissociating in water, it doesn't account for the interactions between H+ ions and water molecules. Let's look closely at the hydrogen atom. When we say H+, we mean that the hydrogen atom has lost an electron. And since the regular hydrogen atom doesn't have a neutron, we see that the H+ ion is really just a proton. And when this really positive hydrogen ion comes in contact with a water molecule, it is attracted to the partial negative side of the water molecule because there are lone pair electrons at the top. And so this hydrogen ion latches onto these lone pair electrons, creating a chemical bond. This is a special type of bond called a coordinate covalent bond, because normally, both atoms donate electrons to the chemical bond, so one from hydrogen, one from oxygen. But in this case, both sets of electrons were donated by the oxygen. So that's why we call it a coordinate covalent bond, to distinguish it between a regular covalent bond. But don't worry too much about this. We'll save that for grade 12 chemistry. All you need to know for now, and the chemical formula that best describes it, is H plus H2O, to show that there's an H+ ion latched onto a regular water molecule. However, to shorten this up, people would typically write H3O plus to show the positive charge, the lack of an electron due to this H+ ion. But if we really want to be super lazy, we just write H+. Alright, so anytime you see an H+, just be aware there's no such thing as an H+ floating around by itself. It will always latch onto a water molecule because it's so attracted to the lone pair electron at the top to form a hydronium ion. The only reason why you're seeing this H+ symbol is because it simplifies things, and also we're lazy. Alright, so Arrhenius did not take into consideration the hydronium ion. The other problem with the Arrhenius theory is that its definition of bases was too specific. So take ammonia, for instance. Ammonia has all the properties of a base. It can neutralize acids. It has a pH above 7. It breaks down organic molecules, so it's often used as a cleaner. It does everything a base can do, but according to Arrhenius, it's not a base because it does not directly release hydroxide ions. There's no OH- in its chemical formula, and that's where Bronsted and Lowry come in. Instead of looking at acids and bases in terms of who can release the H+ ion and who can release the hydroxide ion, they instead decide to focus on the movement of protons. Remember, a proton is essentially an H+ ion, so the definition of acids for Arrhenius and Bronsted-Lowry are essentially the same. Their wording is just different, so while Bronsted-Lowry uses the term proton, Arrhenius uses the term hydrogen ion. Where their definitions differ is with bases. While Arrhenius is focused on the hydroxide ion, Bronsted-Lowry suggested that the base is the one that receives the proton and called it the proton acceptor. So let's take a look back at ammonia again. I like to use this acronym to help me remember the Bronsted-Lowry definition. Big Ale. Base is gain, acid is loss. But gaining and losing what? Protons. The base gains the proton, so it's a proton acceptor. The acid loses the proton, so it's a proton donator. Looking at the top over here, we see that ammonia turns into ammonium. And going from here to here, the ammonia gained an H+ ion. Since the base is the one that gains, ammonia is considered to be a base. On the other hand, going from here to here, the water molecule seems to have lost an H+, resulting in the release of a hydroxide ion. Since acid is loss, water is considered to be my acid. And this is why ammonia has basic properties. It's not that ammonia itself released the hydroxide ion, but it caused the water molecule to release the hydroxide ion for it. And the hydroxide ions that are released during this process is what gives ammonia its basic properties. Alright, so once again, base is gain of a proton, so whoever gains the proton is considered to be a base, while acid is loss, so whoever loses the proton is considered to be an acid. Now, once that base gains the proton, what it turns into is called the conjugate acid. Meanwhile, when the acid loses the H+, it turns into something called the conjugate base. So they've kind of switched roles, where once it was a base, now it's conjugate acid. Where once it was an acid, it's now a conjugate base. So the word conjugate just means partnership, so don't freak out. It's not like you're conjugating verbs in French or anything like that. Dr. and Mrs. Vandertramp is not coming after you here. But the main reason why these are opposites here than what they were before is because many reactions are reversible. You'll find that out in grade 12 chemistry. And if the reaction is reversible, going in reverse, now the conjugate acid is losing its H+, turning back into ammonia. Meanwhile, the OH- is gaining a hydrogen ion, turning back into water. So going backwards, their roles are reversed, and we just follow the acronym again. Base is gain, OH- has gained an H. NH4, acid is loss. It's lost that H+, turning NH3. Alright, so what I want you to do is press pause and try this question out yourself. Tell me which of these is considered to be acid, which of these is the base, which of these is conjugate acid, which one's conjugate base. Alright, press pause. When you're ready, press play, and we'll take it up. Alright, so looking at the before picture, it was HCl. After the reaction is now Cl-. What has happened between here to here? Well, the HCl has lost an H+. Since acid is lost, therefore this HCl is my acid, while Cl- is my conjugate base. Ammonia, on the other hand, has gained an H to become NH4+, ammonium. Since base is gained, NH3 is my base, and ammonium is its conjugate acid. Alright, so NH4+ is my conjugate acid, while Cl- is my conjugate base. Alright, try these two at the bottom. Press pause. When you're ready, press play, and we'll take it up together. Alright, so looking over here, H2PO4 versus HPO4, it seems I've lost something here. Therefore, this one is my acid, while this one is my conjugate base. Over here we gain an H+, so base is gain, and this is my conjugate acid. Looking on this side, HCOH has lost an H, acid is loss, and turns into a conjugate base, while CN gains an H, and base is gain, and it turns into my conjugate acid. Now, some substances can act as an acid or a base depending on who it's reacting with, the most common example being water. So water is said to be amphoteric, although some textbooks may call it amphiprotic. Over here we have HCN, it's lost an H to become CN, making this my acid because acid is loss, and this is my conjugate base. That means water is acting as my base, and hydronium is my conjugate acid. But with the other reaction over here, acetate has gained an H, making it my base, and this is my conjugate acid, while water has lost an H, making this my acid and my conjugate base. So as you can see, in one instance, water is acting as a base, but in another example, water is acting as an acid. So we say that water is amphoteric or amphiprotic. A strong acid or a strong base is one that dissociates completely into its ions when in water. So if you take a look at this situation over here, hydrochloric acid is considered to be strong. So if you had 100 molecules of HCl, once you place it in water, all 100 of them would break up. So you'd have no molecular HCl left over. All of it would break up completely into H+ ions and Cl- ions. But please remember, when we say H+ ions, we really mean hydronium. So in a bucket full of hydrochloric acid, you would have 0 HCl molecules. Instead, you'll just have hydronium floating around and chlorine ions floating around. This is also true for strong bases as well. Now, looking over at weak acids instead, here we have an example of acetic acid, a weak acid, also known as, well, the active ingredient in vinegar anyway. So acetic acid is considered a weak acid because if I had 100 molecules of acetic acid, 99 of them would still stay stuck inside their molecular format. Only one of them would break up, and when one acetic acid breaks up, it releases one hydronium and one acetate ion. So when the acetic acid breaks up, very, very little of it, less than 1%, will actually break up into acetate ions and H+ ions. Most of them will still remain in their acetic acid molecular form. And that is the difference between strong versus weak acids. With weak acids, the H is still stuck in the molecule itself. Only the H's that are free and dissociated are able to chemically react. As long as they're stuck on the molecule itself, they are unable to react. So with weak acids, very few H+ ions are floating around, versus strong acids, since they release all of their H's, there are so many H+ ions floating around, ready to react. That's what gives the acid its strength. So strong acids 100% ionize, that's why we use a single-headed arrow, they 100% break up, versus weak acids only partially ionize, less than 1% break up, and so you'll have an equilibrium being established where most of it will be in the molecular form and very little of it will actually break up. So make sure you're using the right arrow type in your chemical equations. If it's a strong acid or a strong base, make sure you're using the single-headed arrow to show that it 100% dissociates or ionizes. While on the other hand, if it is a weak acid or a weak base, make sure you're using the equilibrium instead. Now, be aware, just because something is concentrated doesn't mean it's strong, and vice versa. Just because it's dilute doesn't mean it's weak. So in this situation, we see a very dilute solution. It's dilute because there's very few molecules floating around. It's not very crowded. However, if you look at it, every single one of these molecules has broken up completely. There are no molecules still stuck together. Therefore, we consider it to be a strong acid. So here we have a strong but dilute acid. Over here, we have all these ions crowded together, and that makes it a concentrated solution. You'll also notice that they are all ions. Every molecule is ionized. There are no molecules left. So that makes it a strong acid. Now over here we have a dilute solution again because it's not very crowded. But notice how two of them remain in their molecular form. Only one of them broke up into their ions. So that makes this a weak and dilute solution. Here we have another crowded solution. That makes it a concentrated solution, but again, very few of them are in their ion format. Most of them are stuck in their molecular format, so that makes it a weak but concentrated solution. All right, so just make sure you know the difference between concentrated versus strong, weak versus dilute. They are not the same thing. One refers to how well it dissociates, how well it breaks up. The other one refers to how concentrated, how many moles per liter, how crowded the solution is. All right, so how do we know which acids are strong and which ones are weak? Well, we memorize them. So for this course, you'll only have to worry about the 6 strong acids. And here is the story I used to remember them. I brought chlorine into the forest. I don't know why, but I just did. Unfortunately, I fell, I tripped, and I spilled all the chlorine everywhere. It was an ecological disaster, killed off all the trees. I come back a few years later to check on the health of the forest. Are the trees growing back? Are they all healthy again? No. So far, so for. No trees are growing. No threes. Only clovers, clovers, are growing in my forest. Alright, so that stupid little story has just helped you memorize the 6 strong acids, because now all you have to do is just add in the hydrogen, hydroiodic acid, hydrobromic acid, hydrochloric acid, this one's an H2SO4, sulfuric acid, nitric acid, and perchloric acid. Alright, so anytime you're dealing with these 6 strong acids, make sure you use the single-headed arrow, because they will 100% ionize into their proton that release and whatever anion happens to be attached to the end. Any other acid that's not listed here, you can consider to be a weak acid, right? And so weak acids, they must use their equilibrium arrow, looking like this. I like to draw my arrows like this to show that less than 1% will break up into their H+ ions and whatever anion happens to be, whereas more than 99% will stay in their molecular format, where the H is still stuck to the molecule, unable to release their ions out into the solution, thus making them weak. For strong bases, there's no need to memorize a story. At that point, it's just essentially the group 1 and group 2 hydroxide. So anyone in group 1 that's a hydroxide, so lithium hydroxide, sodium hydroxide, potassium hydroxide, or any group 2 elements that are hydroxides, like beryllium hydroxide, magnesium hydroxide, calcium hydroxide, etc., etc. Group 1 and 2 hydroxides are considered to be strong. So these strong bases are going to have the single-headed arrow again, 100% breaking up into whatever cation they are, and then the hydroxide ion behind that. If you recall, according to the Bronsted-Lowry definition, an acid is defined as a proton donator. So whichever compound releases the H+ ion is considered to be an acid. However, some acids can release more than 1 proton. So for instance, acetic acid over here is considered to be monoprotic. Right? Monoprotic, remember protic sounds like proton, and a proton is basically an H+ ion. So with acetic acid, it can release this 1 H. And that's why it's called monoprotic. Now some students go, well, doesn't have these other H's, why can't these H's be released? This is known as an acetate ion. It's a polyatomic ion. Polyatomic ions are those groupings of atoms that tend to be very stable together. And because they're very stable together, they tend to react as a group. So this acetate ion very rarely breaks up during chemical reactions. So this H is integral to its stability and cannot just be released as an acid proton. All right, so only this 1 H at the very end can be released. And that's why we typically write acetic acid as CH3COOH to keep this H and these H's separate so that we know it's just this H that's able to be released and not these H's. Sulfuric acid and phosphoric acid, on the other hand, are considered to be polyprotic. Specifically, sulfuric acid is known to be diprotic. Di is the prefix for 2 because the sulfuric acid can release 2 H's. It releases 1 H here, and then from here, HSO4, it can be released a second time. Phosphoric acid is triprotic because it can release 3 H's. It releases an H over here, then it's got 2 left over, which can then be done again. Then it's got 1 left over, which can be done again. Now, if you recall, sulfuric acid is considered to be a strong acid. It's one of the 6 strong acids you have to memorize. Because it's a strong acid, we don't write an equilibrium arrow. We draw a single-headed arrow to show that it completely ionizes. So the H2SO4 breaks up into H+ ions and HSO4. However, HSO4 is not on our list of strong acids. It's considered to be a weak acid. So from HSO4 breaking up into these guys, this requires an equilibrium arrow because this is unlikely to occur. So when H2SO4 dissociates, we call this the first dissociation constant, Ka1. Notice how Ka1 is a very large number because we know that this will completely break up. On the other hand, the second dissociation constant, Ka2, much smaller than Ka1. So going from HSO4 into SO4, that's very unlikely to occur. So if I had a beaker of sulfuric acid, the most common ion or molecule floating around my solution would be H+, because you have a lot of H plus floating around here, and you have some H plus being released over here. The next most common ion you'll have floating around in solution would be HSO4, followed by sulfate, because to get to the sulfate level, you'd have to break up a second time, and that is very difficult to do. Finally, you would have 0 H2SO4s, because all of them broke up during the dissociation. And so this would be the increasing concentration of your ions in solution. With phosphoric acid, because it's weak, very little of it breaks up right off the bat. So the first dissociation constant, very small, but then to get to this next step, it's less and less and less likely. So if each time you're breaking up and less than 1% actually breaks up, then that means in order to get to this step over here, only 1% of 1% of 1% will finally make it to the phosphate level. So that's why the concentration of ions in a solution of phosphoric acid in increasing order would be this. Most of the molecules will be H3PO4 still stuck together because very few of them broke up. Then the next common ion would be H plus ions because they're released here, here, and here, followed by the H2PO4, HPO4, and then finally the phosphate, which is the least likely ion to be floating around your solution. Alright, so typically each dissociation has its own unique equilibrium constant, K1, K2, K3, and they progressively decrease as you go along. Now, we use something called the pH scale to measure how acidic or how basic a substance is. Specifically, the pH scale measures how much H plus ions are floating around inside the solution. In case you want to know, the pH comes from the Latin term pondus hydrogeni, which roughly translates to the potential or the power of the hydrogen ion. Now, this scale goes from 0 to 14. If you want to know why, you'll have to take grade 12 chemistry. But essentially, solutions that have the same number of hydrogens and same number of hydroxides, well, then they would turn into water. And pure water has a pH of 7, so we call this pH neutral, because it's neither an acid nor is it a base, it's both of them together, canceling each other out to create water. On the other hand, if your pH is below 7, from 0 to 7, it is considered to be acidic, while if the pH is between 7 and 14, it's considered to be basic. Now, you don't need to know too much about the pH scale itself, but essentially the scale is logarithmic. What that means is each jump on the scale goes up by a factor of 10. So if I have a solution that's a pH of 2 and another solution that's a pH of 4, this is not twice as acidic, it is actually 10 times 10, so 100 times more acidic. So on a logarithmic scale, each jump on the scale is actually a factor of 10. Same thing. pH of 6 versus pH of 3, it's not twice as acidic. It's 10 times 10 times 10, 1,000 times more acidic. In order to calculate pH, we use this equation over here. pH is the negative logarithm of the H plus concentration. Now just remember, when we say H plus ions, we also mean hydronium too. So you might see the equation being written as pH is equal to negative log of the hydronium concentration. But don't forget that concentration is measured in moles per liter. So let's try out a sample calculation. Plug in 0.1 in the molar concentration over here. So negative logarithm of 0.1, and you should get an answer of 1. Now, depending on your calculator, you may need to push the negative button, then the log button, then 0.1. While other calculators may want you to press the 0.1 first, then the log button, then the negative symbol. Just find out which way your calculator prefers. The answer should be a 1. Now, be careful. Don't press the minus sign when you're trying to press the negative symbol. One is for the subtraction operation, while the other one is for the negative symbol itself. But typically the negative symbol is either a negative sign with a little bracket on the outside, or the word NEG, or it could be plus or minus. Usually it's these three buttons that I see the most often on calculators. But as long as you're getting an answer of 1, you should be doing it fine. Try out B, C, and D and compare your answers at the bottom. If they don't match up, then you're doing it wrong. Come talk to me. But if they do match up, great, you know how to use your calculator. Now, what happens if I want to go the other way around? So instead of searching for pH, I give you pH, and I want to find the concentration of H+. So the opposite of logarithm is exponent 10. So 10 to the power of negative pH gives you the hydronium concentration, the H+ ion concentration. So if you plugged in a pH of 1 over here, it'd be 10 to the power of negative 1, and you should get a 0.1 concentration for the H+ ion. Now, just as there is a pH scale, there's also a pOH scale. The equations are still the same, but instead of negative logarithm of the H+ concentration, pOH is the negative logarithm of the hydroxide concentration. Same down here, the hydroxide concentration is 10 to the power of negative pOH instead. And if we ever need to convert between the two, pH plus pOH adds up to 14. Alright, let's try out some sample calculations. What is the molar concentration of a 2-liter solution of HCl at a pH of 2.7? So I'm trying to find the concentration of HCl given that my pH is 2.7. Since they give me pH, I'm probably going to use this equation to find the H plus concentration. So plugging in the pH of 2.7, I get 2.00 times 10 to the power negative 3 moles per liter is the concentration of my H plus. So here they're giving me one situation, H plus ions, but they're asking me for HCl ions. So that shows me I need to set up a ratio. For every one HCl that breaks up, one H plus is released. Well, if I have 2.00 times 10 to the power negative 3 moles per liter of H plus, and it's a 1-to-1 ratio, then the concentration of my HCl should also be 2.00 times 10 to the power negative 3 molar. Let's try question number 2. 0.6 grams of H2SO4 is dissociated into 7 liters of water. So what is the pH of this solution? In order to solve for pH, we use this equation. pH is equal to negative logarithm of H plus concentration. But there's a problem. They don't give me H plus information, they give me H2SO4 information. So that tells me again I need to set up a ratio between H2SO4 and H plus. Now, as I mentioned before, if you have no clue what to do, first step, convert to moles. Since mole is equal to mass divided by molar mass is 0.6 grams, molar mass of H2SO4 is 98.09, divide the two, and I get 6.11 times 10 to the power negative 3 moles of H2SO4. It then goes on to say that I put this powder into 7 liters of water. Now, a small amount of powder dissolved in a large amount of water won't really change the volume significantly, so I can assume the 7 liters is the volume of my final solution. And since concentration is equal to mole divided by volume, there's my mole, there's the volume of my solution, so my sulfuric acid concentration is 8.73 times 10 to the power negative 4 moles per liter. Now, I know that for every 1 sulfuric acid, 2 H plus ions are released. It says assume 100% dissociation. So if my H2SO4 concentration is 8.73 times 10 to the power negative 4, I can double that amount and turn it into 1.75 times 10 to the power negative 3 moles per liter of H plus ions. I can take the H plus ion concentration, plug it into the equation, and I get 2.76 as the pH of this solution. Alright, let's try one last one. What is the pH of a 0.425 mole per liter sodium hydroxide solution? Now I could try to use this equation, pH is equal to negative log of H plus concentration, but sodium hydroxide is not an acid. It will not release H plus ions. So this equation is not going to be useful for me. However, I can use this equation. And when I rearrange it, pH is equal to 14 minus pOH. And because sodium hydroxide does release hydroxide ions, I can use this equation to solve for pOH. Alright, so before we can plug this into the equation, notice how the equation requires hydroxide concentration, but I'm given the sodium hydroxide concentration. So to convert from one to the other, I need to set up ratios. For every 1 sodium hydroxide that breaks up, 1 hydroxide ion is released. But if I have 0.425 moles per liter of sodium hydroxide, then I also have 0.425 moles per liter of hydroxide ions. I can then plug this value into the equation, and that gives me a value of 0.372. I can then punch it into this equation. pH is equal to 14 minus pOH. pOH was 0.372, and this gives me a 13.6 as my pH. Since any pH above 7 is basic, this does match up with my answer. Alright, and that is our introduction to acids and bases.